folks. So this week I'm about to take my oral qualifying examinations, which are the last barrier to admission to doctoral candidacy at my university, and fingers crossed I pass, fingers crossed then it's only another year at least until I can get my dissertation affirmed. So in a year or two, I will have my doctoral degree in geology. Very happy about that. In fact, if I have sort of calculated the schedule correctly, this will be going up on the same day as my candidacy exam. So that's great. Wish me a good luck on my exam. So I'm thinking back as I'm preparing for this exam to the written qualifying exam I took last year. Now, the written qualifying exam was very intense, and it was like 6 hours. It was sort of split into general reasoning, scientific reasoning questions, and specific questions related to the nature of my research. Now, I'm not even sure I'm legally able to describe some of the reasoning questions, but they tended to be of the sort where you had to come up with a model and make some assumptions. You know, this is a scientific test, but we're saying something like, oh, well, we're going to assume that the Earth is a perfect sphere, and sort of reason from that toward our conclusions. And of course, the Earth is not a perfect sphere, at least on a realist account. The Earth is an oblate spheroid, sort of a bulgy sphere. And there are some contexts in which bulgy spheres actually make the math easier. So I took an atmospheric physics class last semester that I hated, where by assuming an oblate spheroid, we are able to, when trying to work out the balance of forces in the atmosphere, ignore things like centripetal and centrifugal forces. So that's great. But for most purposes, a sphere is even easier. And I thought to myself, are there times when there are even easier models of the Earth that we can use to solve important problems? And I thought back to a problem we had a couple years ago where we had a very big tree in our yard that we were very afraid was going to come down on my grandmother's house. Now, we needed to figure out where this tree was going to fall, and so obviously the problem we had with that was we didn't know how tall the tree was, and it wasn't like, you know, most of the trees in our yard are like 20 or 30 feet tall, and this one was much higher than that, and so we're like, well, how do we figure out how tall it's going to be so we can work out precisely where it's going to land? And I told my dad, who's like up on a ladder trying to measure it with like tape measure and stuff, look, I have a sextant because I'm interested in sailing, and I taught myself how to use it. So what I'm going to do is I'm going to take a tape measure, and I'm going to walk out a certain number of feet from the base of the tree, and then I'm going to lie prone on the ground, and I'm going to sight through the sextant and measure the angle between the base of the tree and the top of the tree using the sextant. Why would I do that? Well, if you remember back to high school trigonometry, you'll know that if you walk some distance from the tree, let's call that distance A, and you get as close to a proper right angle as you can with the sextant, and you measure that angle, let's call that angle theta, then the height of the tree is equal to A times the tangent of theta. So, you know, we did this experiment, and we calculated that it was approximately 40 feet tall, which allowed us to plan taking the tree all the way down. And we were only something like 4 inches off in our calculations for the height of the tree. And so what causes that deviation? Well, obviously the deviation from a true right angle between the tree and the ground, and a deviation between the actual angle and the assumed angle that I measured, theta, right, because of height of eye corrections. I can never get perfectly level to the ground. And between all of that, some error crept in. But I thought about this problem, you know, this is really cool, right? Because we always hear about these practical applications for trigonometry and like trigonometry tests, but here's one that actually worked. And I noticed in that case, I basically assumed that the ground was Euclidean. A completely flat plane. I assumed, for the sake of this experiment, a completely flat Earth. Now, that is to make the computation simpler, since I don't have to account for spherical trigonometry. I just use straight Euclidean trigonometry. And on top of that, the error caused by any deviation from a true flat plane by the curve of the Earth relative to any deviation in calculations just caused by difference in the topography would be irrelevant anyway. But here I am carrying out a scientific process using a pseudoscientific, a flat Earth model. So that, got me thinking, right? There's this interesting tendency, this tension, I should say, between the usefulness of a scientific model and the truth of a scientific model. And that's important. It's probably pretty obvious by now that I'm not really going to make an argument that the Earth is in fact flat. I want to talk about scientific instrumentalism. I've talked about philosophy of science before on this channel, and the basic idea is there are people who have issues with empiricism and science's claims to know things, and I'm one of those people. And one possible solution to that is to say, well, look, maybe scientists don't really know what they claim to know, but that's irrelevant. I ultimately am interested in making useful predictions. We call this scientific instrumentalism. So I don't care what is and what is not true. I don't care if the Earth is round or flat. All I care about is the ability to make an accurate prediction. So that's a position that is instrumentalism. And I would say that probably an intermediate position would be something like a defeasibilist contextualist position. So the idea here is that science gives us highly probable knowledge that is constrained to the phenomenological. It is highly probable that the Earth appears round, that kind of statement. And I have sort of existed most of my time in science sort of in between a defeasible contextual position and a hard instrumentalist position. Here's the thing, if we adopt a hard instrumentalist position, it seems like we're committed to a kind of what is scientific depends on the context. In this case where I'm trying to measure the height of a tree and assume a completely straight plane between me and the tree, flat Earth in this case is a more scientific hypothesis. And that's certainly true for a number of other so-called pseudoscientific theories. We might imagine, using an example of a sextant again, and I talked about this in my video arguing that pseudoscience was largely social, that all the math for that was worked out when geocentrism was the dominant model. So it makes my computation simpler to find my position at sea if I assume the Earth is the center of the universe and the sun goes around it. I can even think of contexts in which intelligent design are completely reasonable and useful, right? So let's say that I'm not a biophysicist. That's not my area of research. But and if you are a biophysicist, do comment on this. I would appreciate your feedback. Where it may be more useful to think of a biological system as having been engineered, and to say the population genetics and fitness and all that, that's irrelevant. We can sort of treat this as something that has been engineered. Maybe the engineer was incompetent, but it could still be viewed as an engineer. It still makes conceptual sense. The other, of course, problem with this idea is not only does, say, a flat Earth and a round Earth both generate useful scientific predictions, but it's possible that the more official scientific theory, the round Earth, is less utile in this position. In other words, according to an instrumentalist account of science, a flat Earth model in this context is actually more scientific than a round Earth or an oblate spheroid Earth. And I don't think that we can really get out of that by appealing to a realist or defeasibilist account of scientific knowledge. Because whereas the instrumentalist is stuck with saying what is scientific depends on the context, the realist or the defeasibilist is committed to saying sometimes pseudoscience is better than science. It's more utile. So there is this fundamental tension between what is scientifically useful on the one hand and what people think is scientifically true on the other. Now, I imagine you might be thinking, well, look, we can be instrumentalists, but we should prioritize what is globally the most instrumental. But I'm not entirely sure that works either. It seems like there are a lot more times when a flat Earth calculation is going to be more useful than an oblate spheroid calculation. How many times do we have to calculate Euclidean distances where the deviation between a true flat plane and the manifold that is the Earth is irrelevant? It seems like there are more times when the flat Earth model is more useful. maybe instead of viewing this as a philosophical problem, where pseudoscience is more useful than science on the one hand, or pseudoscience is science on the other hand, we view this as a moment to develop tolerance for diverse positions within the scientific community, of saying, look, in this context, it's perfectly permissible to embrace, say, intelligent design or geocentrism or the flat earth. Not in all contexts, obviously, and not all theories will have contexts in which they are computationally useful, but there are things that we consider legitimate scientific disciplines, like sociology, that you can make a compelling case don't make any useful predictions at all. So it's entirely reasonable to believe there's a context in which flat Earth is a more useful scientific model than anything any sociologist has ever come up with. I don't know whether that says more about flat Earth or about sociology, but it's something to think about. Well, that's going to be it for me this time, and hopefully we'll be back to scripted and rehearsed videos next week. Until then, have a nice day, folks. Bye-bye.